Hi folks, today we're going to talk about the laws of logarithms and work some problems using those laws of logarithms. So we're going to get started. Our first problem, if our log base 4 of x equals 17, our log base 4 of y equals 3, and our log base 4 of z equals 9, then can we determine this log base 4 of x times y divided by z? Well, one route you can do is actually just brute force and try and calculate what x equals, what y equals, what z equals. But a little bit more elegant is using a format is using that laws of logarithms. And so let's see that in play. So we begin with our log base 4 of x times y divided by z. Notice you can use the quotient rule for logarithms because we have a quotient, we have a fraction bar right there. So this can separate it into two logarithms. So the numerator is the x times y, the denominator is z. So the quotient rule states that we'll break this up into log base 4 of x times y minus log base 4 of z. Now, this is almost in the format that we need. We have the log base 4 of z equals 9. We'll use that in just a little bit. But the log base 4 of x times y, we don't have that product itself. But what we do have is log base 4 of x equals 17 and log base 4 of y equals 3. So we can use the product rule for logarithms on that log base 4 of xy. And so that breaks up into log base 4 of x plus log base 4 of y, and then we'll just leave that minus log base 4 of z right there. And so now it just becomes a plug and chug problem. So log base 4 of x is 17, as we mentioned before. The log base 4 of y is 3, and then the log base 4 of z is actually 9. So we have 17 plus 3 minus 9, and notice that equals 11, and we didn't even have to touch a calculator. We didn't have to actually compute x, y, or z. Just showing you how beautiful these laws of logarithms can be. Okay, moving forward into the next problem. So if we have the log base 3 of x equals 6, the log base 3 of y equals 4, and the log base 3 of z equals 12, can we determine the log of x, base x, of z divided by y? So this seems a little bit trickier, but now we're going to toss in a change of base formula along with our quotient rule. So when we have the log base x of z divided by y, what that becomes, just using our facts that we have a log base 3, we can use our change of base formula. This is the log base 3 of z divided by y divided by the log base 3 of x. So all we did is just use our change of base formula at this point. Okay, so now moving to the next part, how do we break it up into where we can use that log base 3 of z and that log base 3 of y? Well, in the numerator, we can break up that single logarithm, log base 3 of z divided by y, using that quotient rule for logarithms, and so that becomes log base 3 of z minus the log base 3 of y, and then we'll leave that log base 3 of x in the denominator. Okay, now we have the values for each of those, so this becomes just log base 3 of z is 12, the log base 3 of y is 4, and the log base 3 of x is 6. So we have 12 minus 4 divided by 6, which is 8 over 6, or 4/3. So notice we didn't have to use a calculator once again, power once again of laws of logarithms, and then we also came into play with the change of base formula. That was our first step. And by the way, you didn't have to use that on your first step. There's multiple methods of getting there. So, but this is just one of them, and it was a direct route. So just because you might solve it a different way doesn't mean it's the only way. So moving on to problem 3. Simplify 3 times the log base 9 of 5 minus x minus 2/3 times the log base 9 of the quantity 25 minus x squared raised to the 6th power minus 1/2 times the log base 9 of the quantity 5 plus x to the 4th into a single logarithm. Whew. So we start with that whole hot mess there, and we're going to try and work with it. So the first thing we can do to make this a little bit nicer, notice how each logarithm term, I should say, has a constant out in front of that logarithm. So there's a power rule that says we can take those constant terms and put them up in the exponent. And that's exactly what we'll do with our first step. It doesn't have to be our first step, but it's probably going to be the easiest route for us. So this becomes that 3 goes up into the exponent, so you get log base 9 of 5 minus x, that quantity, cubed. And then in the next one, notice you see 6 times 2/3 up in the exponent of that quantity 25 minus x squared. The reason why is when you take an exponent raised to some exponent, you can just multiply the exponents. So when we had 25 minus x squared to the 6, and we take that quantity and take it to the 2/3, that's why you just see the multiplication there. And then we subtract off that log base 9, we bring that 1/2 up into the exponent, you get the quantity 5 plus x to the 4 times 1/2. And doing a little simplifying with those last two exponents, you have 6 times 2/3 is 4, and 4 times 1/2 is 2. So we can write that a little bit simpler format. Now, moving forward from there, where can we go? Well, if you look, there's a minus sign in both those last terms. Just to brush it up, it might be kind of tricky when we have minuses because quotient rule will say that goes in the denominator, and what's happening when we have two minuses. So we'll just brush it up a little bit nicer, factor out the minus sign from both, and now notice it looks a little bit easier format for us to work with. Log base 9 of 25 minus x squared, that quantity raised to the fourth, plus log base 9 of 5 plus x, that quantity raised to the second. Now, we can use our product rule for logarithms in those last two terms because you see that plus symbol right there between the log base 9 of 25 minus x squared to the fourth and that log base 9 of 5 plus x, that quantity squared. So combining those into a single logarithm, you get log base 9 of 5 minus x, the quantity cubed just remains the same, minus, that becomes a single logarithm, so the log base 9 of the quantity 25 minus x squared raised to the fourth times the quantity 5 plus x squared. Okay. Now we can use our quotient rule because you just have a minus sign, and so that last term that we just spoke about, that'll go in the denominator of a fraction with a single logarithm out in front of this. So log base 9 of the quantity, you have 5 minus x, that quantity cubed, up in the numerator, and then once again the 25 minus x squared, that quantity raised to the fourth, and the quantity 5 plus x to the second, both appearing in the denominator. So where do we go from here? It might seem like we're done. We do have it into a single logarithm, and that's acceptable. But if we want to brush it up, make it look real nice, we can actually do that as well. So let's simplify this a little bit. Notice 25 minus x squared is just 5 minus x times 5 plus x, those two quantities, and then we have raised to the fourth because that 4 was out there before. So this now becomes, if you just distribute that fourth to each exponent of each factor, you have log base 9 of, you have a 5 minus x, the quantity cubed in the numerator, you have a 5 minus x to the fourth and a 5 plus x to the fourth just from that distribution, and you have another 5 plus x squared. So notice the 5 minus x cubed in the numerator and the 5 minus x to the fourth power, I should say the quantity of 5 minus x cubed and the quantity 5 minus x to the fourth, those should cancel out, and so what we're left with is log base 9 of 1 over the quantity 5 minus x, and then combining the 5 plus x to the fourth, that quantity 5 plus x to the second, we can actually combine that and make it the quantity 5 plus x to the sixth. And then now we'll use the quotient rule one last time. This is the log base 9 of 1 minus the log base 9 of 5 minus x, that quantity, and the quantity 5 plus x raised to the sixth power. And you might say, well, wait a second, we just broke it up. We want it in a single logarithm. Well, log base 9 of 1 is actually 0, so you're left with a much simpler format, negative log base 9 of the quantity 5 minus x times the quantity 5 plus x raised to the sixth power. So all of these formats, with the exception of the second to last one, would have been fine for this answer. I just want you to see some multiple layouts, and all of them are actually equivalent, even though they look quite different from one step to the next. So just showing you how laws of logarithms can actually play some tricks on us in some cases. Okay, moving to the fourth problem. Let's determine whether the following statement is true or false for all possible values of x and y. So we have the log base 8 of x minus y equals log base 8 of x minus log base 8 of y. So what happens here? Well, most people think that the logarithm actually distributes. Well, you can see pretty easily that it actually doesn't. So if we let x equals 2 and y equals 1, then log base 8 of x minus y, well, that be the log base 8 of 2 minus 1, which is the log base 8 of 1, which we know from one of the properties of logarithms is 0. Moving in the other direction, let's try it for the log base 8 of x minus the log base 8 of y, see what that equals. Well, when we plug in 2, we get log base 8 of 2 minus log base 8 of 1. Log base 8 of 2, well, you can write that as 1/3 because 8 to the 1, the cube root of 8 is essentially 2. So, and the cube root is denoted by the 1/3 power. So that's where that comes from. And so you get 1/3 minus log base 8 of 1 we just discussed is 0. So even as soon as you saw log base 8 of 2, you knew that was a non-zero number, and the other part was 0. So you get some non-zero number, and that tells us these are not going to be equal. So one side equals 1/3, the other side equals 0. So we found a counterexample. So that means these two do not equal, and so we have a false statement here. Okay, and so when we look at this, though, just an FYI, the laws of logarithms, what actually happens is the right-hand side becomes log base 8 of the quantity x divided by y. And so the only way these two were to be equal, using that one-to-one property, is that x minus y equals x over y. So there's only some rare instances where these actually do equal. You can't just toss in x and y values willy-nilly there. So moving forward to the fifth problem, determine whether the following statement is true or false for all possible values of x and y. We have log base 2 of x divided by y equals log base 2 of x divided by the log base 2 of y. This is also a common error that occurs when trying to apply laws of logarithms, so that's why I want us all to see it here. So this is, if we let x equal 1 and y equal 2, log base 2 of x divided by y should be the log base 2 of 1/2. Well, notice 1/2 is just 2 to the negative 1. And so that means the log base 2 of 2 to the negative 1, you can use properties of logarithms once again, and that just equals negative 1. However, when we change it up, if we do log base 2 of x divided by the log base 2 of y, what do we get? Well, we get the log base 2 of 1 over the log base 2 of 2. Well, log base 2 of 1 is 0, and the log base 2 of 2 is 1. So you get 0 divided by 1 is 0. 0 does not equal negative 1. So now we have something that falls apart once again. So this means they're not equal, and we have a false statement once again. So just keep an eye on those laws of logarithms. Make sure you're using them correctly. That's the big advice that I have for you when it comes down to it.